We're now going to talk about gases and their kinetic theory. So with gases, we know that gaseous particles have a high degree of molecular motion. And so this is due to kinetic energy. So because the kinetic energy provides each gaseous molecule with energy, they're able to move around quite easily and quite effectively. And so these particles are going to be in constant motion, and they're going to undergo collisions due to this constant motion because they're all moving around so quickly that there's no possible way that they're not going to collide. And so they're going to be undergoing these collisions with other particles, but also the surface of the container which they are contained within. And so if they're not contained within a container, they'll just be colliding with things in the area around them. And so temperature is going to be a measure of the average kinetic energy of all of the molecules in a particular system. So the way in which the purpose of measuring temperature in a lot of chemical applications is to determine how much chemical energy and how much kinetic energy is present in that system. And it's also a way which we measure how much kinetic energy or how much chemical energy are we providing to this system. And so hence, due to this, as our temperature increases, the average molecular kinetic energy is going to increase. And this is because the frequency and the magnitude of the particle to container or particle to surrounding objects collisions is going to increase. And so the particle container collisions are going to be measured as pressure, or particle to surroundings collisions, and these are measured as pressure. And so we can consider this diagram on the bottom left. The more particles which you have in there, the higher the pressure will be, because there's going to be more rebound from the edges of the container. And so we can also see that with the bottom in the blue and red diagram, where on the bottom left we've got lots of blue particles, and so the lots of blue particles, they're all going to be colliding a lot, and they're going to be colliding with the container a lot, and so there's going to be quite high pressure in there because there's not a lot of space for the gas to occupy. Whereas if we look at the red on the right, we can see that there is a lot fewer particles for the same amount of space. And so if we have a lot fewer particles in the same amount of space, that means that we're going to have a lot lesser collisions, a lot less frequency, and a lot less magnitude of these collisions. And so there's going to be a lot lower pressure. And so because there's a lot lower pressure, they'll also be correlated with a lot lower temperature. And so we can see that increased temperature is then going to result in an increased pressure when we're considering a system of constant volume. And so we can now make assumptions about ideal gases. And so an ideal gas is a theoretical gas that abides perfectly by the ideal gas law under all conditions. And so all conditions referring to temperature and pressure, and that's also going to be at a constant volume. And so these ideal gas assumptions are purely just assumptions, and they're ideal. So what we know about ideal gas assumptions is that real gases don't behave in that way at all, and typically don't belong to the ideal gas criterias. But we do need to know the assumptions of ideal gases, because we can apply concepts surrounding the assumptions of ideal gases to our understanding of real gases. And so our main assumptions of ideal gases are that the collisions between gas molecules are elastic, and the molecules are going to have frictionless motion. so they don't lose any energy ever. And so we know that this is not true with a real gas, because the collisions are not going to have frictionless motion and energy will be lost when these molecules collide. The second one is the total volume of the individual molecules on their own is significantly smaller than the volume that the uncompressed gas actually occupies. So this is commonly applied to real gases because we know that the gas that it occupies is going to be a lot smaller, because when we consider the gases, they're all going to be, the gas molecules move around a lot, and so if we're taking gas as a substance, it's going to occupy a lot more area due to its movements than the individual molecules themselves, because the individual molecules themselves are going to be quite small, but once they're moving around, they're taking up more space in order to maintain their gaseous state. So if we were to overly compress them, they would likely be able to compress into a liquid, and that's obviously then directly correlated with that temperature increase as well, because we know as temperature increases, it can likely compress to a different state. And so the third one is there are no intermolecular forces acting on the molecules or their surroundings. And so with ideal gases, that is our assumption. However, we know that with a real gas, there's always intermolecular forces acting on every molecule, whether that just be dispersion forces or whether that actually include like our dipole-dipole interactions and our hydrogen bonding. And so we know that the real gas is going to behave a lot more differently than the ideal gas, because if there's those attractions between the molecules are more likely to clump together in a way, although in their gaseous state, because they are quite movable and quite kinetic, they're obviously not going to clump together as such into a solid, but they will have relative attraction to them, unlike in an ideal gas where they're all going to stay fairly evenly spaced apart. And our fourth assumption is that the molecules are always moving and that the distances between all of the molecules in the gas are going to be greater than the average size of the molecules. And so we know that the first part is definitely true, because we know that gaseous molecules are always moving. We know that all molecules are always moving. Even in a solid, we still have those small movements. But we know that gaseous molecules are particularly kinetic and move quite a bit. However, we know that the distances of all the molecules in the gas are not always going to be greater than the average size of the molecules. And that's because in an ideal gas, we're assuming that the gas molecules are not really moving around significantly. However, in a real gas, we know that the molecules are moving a lot, and they have motion in which they're going to be colliding excessively and then losing energy from that point. So upon those collisions, obviously the distance between the molecules is going to be changing and is going to be coming closer. And so that part doesn't necessarily apply to a real gas. And so as a result of all of these assumptions, we can come to the conclusion that gases cannot become liquid at room temperature. And that's just based on the assumptions of the ideal gases and how we can apply those to real gases in order to then know that they can't become a liquid at room temperature, despite not fully following the ideal gas laws. And so when we consider gases, we need to consider the variables which describe gases. And so we have four main variables, which these are. And so these include a number of gas molecules, which will be measured in moles, temperature, which is measured in degrees Kelvin. So that's really important to note, is that the temperature is in degrees Kelvin as opposed to degrees Celsius. So that's really important to remember for any calculations involving pressure. The volume, which is measured in liters. So that's also really important to remember with calculations, is that it's liters, not milliliters, because many questions will give volumes in milliliters. So you want to make sure that it's in liters. And pressure. So that's going to be measured in kilopascals. And so when we're considering the number of gas molecules, we need to consider that increasing the number of gas molecules will subsequently result in an increase in the pressure. And so this is because if we have more gas molecules in a system, there's less space for them to uptake, and so they'll be all compressed in one area, which means that there's more pressure acting on them. And that's correlated with the volume. And so with the volume, increasing the volume will decrease the pressure, because as the volume of the container gets bigger, there's then more space for the gases to occupy. And so if there's more space for the gases to occupy, then they can move around more, they're more spaced out from each other, and so there's less compression onto those molecules. And so next we can look at temperature. So increasing the temperature will increase the pressure, and that's because when we increase temperature, we are increasing the movement of the molecules in the gas. And so when we're increasing the movement of the molecules of the gas, there's more kinetic energy, and so the molecules are more frantically moving around. And as they're more frantically moving around, it means that there's, at any given time, although there's the same amount of space in the container, it appears that there is less as the molecules are moving more quickly through that time. And finally, we've got pressure, in which the pressure will be affected by any of the above variables and will opposingly affect those variables. So with number of gas molecules, as those increase, the pressure will increase. With temperature, pressure will increase. And with increased volume, pressure will decrease. And then pressure will opposingly affect those variables. So if we increase pressure, we'll need to have less gas molecules in order to do that, or less gas molecules per the amount of area. For temperature, we'll need to decrease the temperature if we decrease the pressure. Same as if we decrease the pressure, it will decrease the temperature. For volume, we'll need to, if we decrease the pressure, it will increase the volume of the container which the gases are in. Same as if we increase the pressure, it will be a decrease in the volume that the gases are in proportionally. So now we have our gas laws. And so we have four main gas laws. And so we have three gas laws which are individual gas laws, and then we have a combined gas law. And so the three gas laws which we have, which we combine, are Boyle's law, Charles's law, and Gay-Lussac's law. And so when these all are combined, we end up with what we call the combined gas law. And so these gas laws are commonly used to compare those variables which we talked about earlier, and to show the proportional changes that occur mathematically. And so it can help us determine the volume of a particular gas, the temperature of a gas, or the pressure of a gas, if we know one or more of the variables. So Boyle's law is going to consider the volume that a gas occupies, and that will be inversely proportional to the pressure applied to it at a constant temperature. So our formula will be P1V1 equals P2V2. And so this is typically used if we want to find the pressure of a gas and we know the volume of the gas, or if we want to find the volume of a gas and we know the pressure of the gas. Our next one is Charles's law. So Charles's law is the volume, talks about the volume that a gas occupies and it being directly proportional to its temperature. And this is only applied when at a constant pressure. And so we will typically use this if we want to determine the volume of a gas based on the fact that we know the temperature, or if we want to determine the temperature of a gas based on knowing the volume. Our final one is Gay-Lussac's law. And so this is considering pressure and temperature. And so it's considering that pressure is directly proportional to temperature at a constant volume. So without changing the volume, if we increase pressure, we're going to increase temperature. And so we use this formula if we know the pressure, but we want to find the temperature, or if we know the temperature and we want to find the pressure. And so it's important to note that for all of these, they have to be used in conjunction with a reaction. So if we know a starting pressure, a starting volume, and then a finishing pressure, we could use Boyle's law to find the finishing volume. Or if we knew a finishing volume, a finishing temperature, and a starting temperature, we could determine the initial volume using Charles's law. Or for example, considering Gay-Lussac's law, if we knew a starting temperature, a finishing pressure, and a finishing temperature, we could determine the initial pressure. And so, as mentioned before, when we combine all of these, we get the combined gas law. And so, the combined gas law has a formula of P1V1 over T1 equals P2V2 over T2. And so this basically provides us with a combination of all of the above in order to then determine a multitude of different variables. And so I would say this is one of the most common ones which you will use when considering the gas laws, because it encompasses so many different factors that affect the gases. Another important thing we want to note is the molar volume of gases. And so this is because 1 mole of gas at standard temperature and pressure, so STP conditions, will occupy a volume of 22.7 litres. And so this will always occur regardless of anything other than the fact that it must be at standard temperature and pressure. And so this means that we can use this formula, which is N equals volume divided by 22.7. So this means that if we don't know the number of moles of a gas, but we know the volume, we can determine the number of moles. Or if we want to know the volume, but we know the number of moles, we can determine the volume using this formula. So we also want to consider this formula here, which is the ideal gas law. And so the ideal gas law is PV equals nRT. And so the combined gas law is containing all 4 variables which we looked at before. So that being temperature, pressure, volume, and number of molecules. Then we also need to consider that we're considering Avogadro's number. And so that's that 1 mole of gas occupies 22.7 litres at STP. So STP being 101.3 kilopascals and 270 degrees Kelvin. And so incorporating this value is going to yield the ideal gas law. And so we can see in our ideal gas law, P is going to be the pressure in atmospheres. V is going to be the volume in litres. N is going to be the number of moles. R will be the universal gas constant. And so the universal gas constant is basically just a constant which represents the amount of gas raising a temperature per mole. And so that's 8.3145 joules per mole per degree Kelvin. And then we have temperature, which we need to importantly remember is in Kelvin. And so there are variations from the ideal gas law, and so we briefly spoke about this before, but we're going to consider this in more detail. So gases will behave in an ideal way under high temperatures and low pressures. And so the gases will depart from these ideal conditions at low temperatures and high pressures, because this is going to violate the assumption that there is significant space between the molecules and that their volume is negligible. So we can plot this differentiation by comparing PV over RT to the pressure. So that's comparing the pressure times by the volume divided by the universal gas constant and our temperature. And so that can then be compared with the pressure as a proportional value, and that helps us to determine what our departures from the ideal gas constant will be. And so we can see based on this diagram here, it's actually really hard to achieve the ideal gas conditions as it only occurs for a very short amount of time. And so it will only occur at a pressure of 0 and then for some other gases occurring at various other pressures along the way, but only for a very brief amount of time. So we can see that there is often variation from the ideal gas law, and the ideal gas law is often not followed through.